Good evening and welcome to the problem solving session 6 of the course
Good.
Microwave Engineering. Today's session will be trying to cover some sample problems and some conceptual questions from the content of week 6. As you all know, these are some of the topics which had been discussed in week 6. The initial lectures were on power dividers, the different types of power dividers, especially the T junction power divider, the resistive power divider, and a Wilkinson power divider. Then coming to directional couplers, wherein you have seen video lectures where you have seen how to define the different parameters like coupling, directivity, isolation, and insertion laws. And there had been a discussion on the working principle of two-hole directional coupler. And also towards the end of this week 6 content, the last lecture was focused on microwave filters, wherein you come across the filter design with the insertion loss method. And you have seen the different responses like a Butterworth filter or a Chebyshev filter or a linear phase filter, etc. So to start with, I would like to have some questions and to understand if you could to understand whether you got the concepts right. So I will also try to just give a small, short, or very brief idea of what each of them are, but it's not a detailed analysis or study. We are just brushing up the concepts so that it will be easy for us to go to the numericals. So to start with power dividers, as the name suggests, you know what a power divider is. Say you have a device wherein you can divide. Say if you have an input port and you can divide that into two, say 2 and 3, port 2 and port 3, wherein I can say some constant alpha times P in. That means how much the input power was there, alpha times of that is being delivered to the port 2. And how about the port 3? It should be 1 minus alpha Pi, provided it's all lossless power divider. Okay, so this power dividers could also be used as a power combiner, wherein you see, so this is a divider. Suppose if we use the two ports here to input some power, and we will get the at the third port the combination of the two inputs. So so the same power divider circuit could be also be used as a power combiner circuit. Now straight away going to power dividers, which you have which you have come across in the video lectures. First is a T junction power divider, and it's lossless power divider. Okay, so let's see how it is. Say you have a network like this, so it could be modeled as like a transmission line setup. So as you see, this is Z0, this is say 2Z0, and this is 2Z0. So if the input impedance is 2Z0 and 2Z0 in both the arms, say if this is P called as port 2 and this is port 3 and this is port 1, uh, will the power be divided equally among port 2 and port 3? Do you agree with that? Say if I have P in, will it be equally divided between the port 2 and port 3?
Yes, ma'am.
Yes. So here you will get P in by 2. Here you will get P in by 2. Okay. And how about the matching here? So Here S11 is 0, which indicates that at port 1, excuse me, at port 1 you have perfect matching, whereas at port 2 and port 3 it's not perfectly matched. And also if I take S23, S32, that is the isolation between port 2 and port 3, that is, it's not isolated. That means it's not equal to 0. Okay. So these are all the facts or very brief idea about the lossless T-junction power divider. Now let me quickly go to resistive divider. Okay, coming to resistive power divider, you have something like this. Say port 1, port 2 and port 3. Say this is Z0 by 3, this is Z0 by 3. Say this is also Z0 by 3. So here, what is the speciality here compared to a lossless T-junction power divider? What is peculiar about the resistive power divider? Okay, let me ask you the first question. Will the power be equally divided here as well? Say if you
Yes.
have, yes, here it will be equally divided. But will it be P in by 2? That's the question. As it was in the T-junction power divider, will it be P in by 2 here as well?
I think no. I
No.
think no.
Yeah. So there, if you notice here, there is a resistive network wherein you have a dissipation in that resistive network, which will actually make this as P in by 4. Okay. So at the port 3, if you measure, you will get P in by 4. Basically, it is dividing equally, but at the port 3, because of the dissipation in this, so a P in by 4 is getting dissipated here, another P in by 4 is getting dissipated here. So totally because of the because of the uh, because of the resistive network here, you have a dissipation. Therefore, it is not P in by 2, it is a P in by 4. Now, how about the reflection coefficient? S11, S22, S33. So, other way to ask this is, are they perfectly matched at all the ports? A resistive power divider, are they perfectly matched? At port 1, port 2, port 3. So, I hope you remember S11 is indicating the reflection coefficient at port 1, which says if it is 0, it's perfectly matched. So, I believe you remember that this all the 3 ports are perfectly matched in case of a resistive power divider. And how about the isolation between port 2 and port 3? Are they isolated? They are not.
Yes, ma'am.
They are not isolated. I'll tell you why. So, have you noticed the 2 ports are being kept open? It's not connected. So, now we will be coming to something called as Wilkinson power divider. Probably you will be remembering between the 2 ports there was an impedance. Okay. So, that makes the ports, between the port 2 and port 3, that gives an isolation. Okay, so I will quickly go to the Wilkinson power divider also. So in Wilkinson power divider, you have basically a 3-port network wherein, so this length is going to be lambda by 4. That means the quarter wave length. Okay. and so you know that this is Z naught and this is Z naught. So what should be this quarter wave length, quarter wave lines impedance? It should be root 2 Z naught. Okay. Then if you are remembering, there is another resistor connected between these two, that is 2Z naught. Okay, this is the one which gives isolation between the port 2 and port 3. Here I have S23 S32 equal to 0. Okay, and same like your resistive power divider, all the three ports are perfectly matched. Okay, so this is something all some basics of the different power dividers. So let us now quickly go to some quick questions. Okay, so that we'll just see if you could understand the concept. Okay, coming to the first question, I appreciate if you could answer them in the chat, or you can unmute yourself and answer it. These are very simple questions just to refresh the concepts. Power dividers and couplers are microwave components used for power division or power combining. Okay. Are they passive, active, linear, or non-linear? What do you think?
D option. No.
Are they passive, active, linear, non-linear? So,
Non-linear.
okay. So, why do you think it's non-linear? Or I can ask you like this: when do you say something is something is giving you a linear response, or say if you have an input and in output, say output, if the output is proportional to input, say, then we call it as a linear device. If not, we call it as a non-linear device. And how do we differentiate between active and passive? If you remember, active means if you have some sources, or if it generates some power, or if it stores some energy, then we call it as active. So how about this power dividers? Are they active or passive?
Passive.
Yeah. So it's a passive device. We cannot specify about the linearity or non-linearity here, because there is no relation. I mean, the relationship between the different powers. As you see, if you have a power divider like this, basically the output is going to depend on what is these arms. What are these arms? Say, if you have the impedance here, so this power division is going to depend on the nature of the arm. If you have, say, if it is a resistive network, it will depend on the resistor connected. Okay, or if it is a simple transmission line, it will depend on the characteristic impedance of that line. Okay, so we can't give a no say we can't say whether it is linear or non-linear, because it's not coming into either of the categories. Now, coming to the second question, T junction is an example for very simple question: 2 port, 3 port, or 4 port?
3-port network.
Okay. Coming to the next question, if a device is passive and contains no anisotropic elements, then the device is what kind of a network? So, device is passive. That means there is no energy storage, there are no sources. So isotropic, it's like equally in all directions. So if it is, so no anisotropic elements means you have isotropy. So can we call that kind of a network as a reciprocal network? Or let me tell you this. What do you mean by a reciprocal network? Suppose if you interchange, say you have two ports, input port and output port. If you interchange those ports, it will have the similar response. If that is the case, we call it as a reciprocal network. So if it is a passive device with no anisotropic elements, what do you think? Is it reciprocal, non-reciprocal, lossless, or lossy device? Okay, so it's a reciprocal device. Obviously, if there are some if the device is active, or say if it has a L or C components, it is going to be dependent on whether it's going to be dependent on the energy storage, and it cannot be a reciprocal device. Okay, because it's mentioned very clearly the passive nature and no anisotropic elements, we can say that it is reciprocal. And you know that it follows the symmetry property. Sij is equal to Sji. Now, this is again a connected question. I hope you can answer it easily. Scattering matrix of a reciprocal network is, yes, right answer.
Symmetric.
It is symmetric. Now, if all the ports of a microwave network are matched, then the diagonal elements of the S matrix of the network is 0. So please remember what are the diagonal elements in an S matrix. So if all the ports are matched, perfectly matched, then can we say that all the diagonal elements are 0? Any answers? It's a true or false statement. So I hope you remember what I told about this reflection coefficients at port 1, port 2 and port 3. If they are perfectly matched, these are going to be 0. So basically these are in a 3 cross 3 matrix, these are the diagonal elements. Okay. So it has to be 0. It's a true statement. Okay. Now coming to the next question. Directivity of a directional coupler signifies the direction of power flow in the coupler. Is it signifying the direction of power flow? What is directivity in a directional coupler? So I think I haven't mentioned some basics of directional coupler, but still you can try. Okay, let me just go through some more questions on T-junction power dividers, and then we'll come back to the direction coupler. Okay, a T-junction power divider can only be used for division of power. Is it true that a power divider can only be used for dividing the power? Can it not be used for combining the power? So if you have this
And also combine.
yes, it can also combine. So this is false statement. It can also be used for combining the power. Okay. Now, a lossless T-junction divider can be modeled as a junction of 3 transmission lines. True or false? I hope you remember the lossless T-junction divider. Can we model it like a three transmission line? The junction of 3 transmission.
True.
True. Okay. For the realization of lossless T-junction power divider using transmission lines, the characteristic impedance of the transmission line has to be real. So if you remember, in a lossless T-junction power divider, there was something like, so we used to have this junction of three transmission lines, wherein you remember I had drawn like this, like 2Z0, 2Z0 and Z0. So this impedance of the transmission line, I mean the characteristic impedance of these lines, should it be real? I mean, can it be complex? Is it okay to be complex? So please note, there is a statement here. It's a lossless T-junction power divider. Can we have it has to be real, or it can also be complex? What do you think?
Yeah.
It has to be real, because if it is going to be complex, there will be L and C, and there will be energy storage and some amount of, so it cannot be later called as a lossless T-junction power divider. Okay, so it has to be real. Now coming to the fourth question here, the output power measured at the two ports of the T-junction. Say you have two ports. Okay, so I will say this is P2. I am measuring the power P2. I am measuring the power P3. Okay. Is it a constant power, or can we vary the power? It's not a real power. Which among these are true? So to answer this question, you have to think what this P2 is going, or P3 is going to depend on. P2, P3 is purely going to depend on the nature of this transmission line, nature of the impedances of the transmission line. So can we change it, or it will be always be say equal power division? Simple way to ask it. Will it be like always P2 and P3 is equal to P1 by 2 always? Or so that means it's a constant. Or can we make it different?
Variable.
Yes, so it's variable, and it's going to depend on the impedances of these transmission lines. That's the key takeaway here. Okay, now coming to a small simple numerical. If the input power is divided in the ratio 2:1, okay, so I have a T junction like this, and the power, say P2, P3, it's in the ratio 2:1, okay, and the characteristic impedance of the two output lines. Okay, I have two output lines. One is having a characteristic impedance of 150 and the other is 75 ohm. Tell me what is the impedance of the input line. What should be the input impedance of this network? You can see that there are two transmission lines, 150 ohm and 75 ohm. Are they connected in parallel?
Yes, in parallel.
So can we say Zin is 150 parallel 75?
Okay. 90 ohm.
Is it coming 90? Yeah, it's 50. Right. Okay. Now, the diagonal elements of S matrix of a resistive T junction. So, the resistive power divider. Diagonal elements. You know the diagonal elements S11, S22, S33. Resistive power divider. Zero. Right. Okay, just one more question at last. What is the major disadvantage of a lossless T junction power divider?
Ma'am, please repeat previous question.
Okay, so this was about the resistive T junction. So in resistive T junction, if you remember, I have told all the 3 ports are perfectly matched. So you have the reflection coefficient value to be 0. So that's about the diagonal elements of the S matrix. Okay.
Yes, sir.
Okay, so a quick recap of this. What is the disadvantage of a lossless T junction power divider? Or why do we, or what is more better in the resistive power divider or a Wilkinson power divider? So if you remember the lossless T junction I told, so you have the transmission lines like this, 2Z0, 2Z0 and Z0, and we saw that only S11 is 0, but S22 is not equal to 0, S33 is not equal to 0. So you know that it's not matched at all the ports. Whereas in case of a Wilkinson power divider or resistive power divider, you have seen already that all the 3 coefficients, that is S11, S22, S33, all 3 are 0. So that means it's matched at all the 3 ports. Okay. Okay, now there is a question on Wilkinson power divider. For an equal split Wilkinson power divider of 50 ohm system impedance, the characteristic impedance of the quarter wave transmission line used is. So you remember what is Wilkinson power divider. This has a impedance of 50 ohm. So you have this quarter wave transformer here. So basically this is the quarter wave transformer, lambda by 4. So it's equally dividing the power. That's the key here. In that case, what will be this ZQWT? It's a basic idea of this. So this is going to be root 2 Z0, root 2 into 50. So it's going to be 70.7. Okay.
Madam,
Yes.
hello.
Yes, please.
Madam, that quarter wave, madam, one doubt, madam. Madam, for quarter wave input impedance is there, no? That root of Z not into Z in, madam.
Okay.
Hello.
Yes, please.
Madam, this formula is root of Z naught and Z in. One more formula is there, no, madam, for quarter wave transformer.
Quarter wave transformer, if you are talking about what we saw in transmission lines,
Uh,
in transmission lines, we use a quarter wave transformer, okay, to match, say, you have a load ZL and you have some, this is the transmission line, and here you have some impedance, say something like Z0 or something like that, okay. So this is the quarter wave transformer. So this will be square root of Z0 into ZL. Here what we are trying to do, we are trying to
yes,
match
ma'am.
Z0 to ZL. Is that what you are asking?
Yes, ma'am. This formula only I am searching. But two is it not you told no? But I don't know, madam. Based on the questions, I cannot find out formula. Here formula is different. No, root two into is it not? Depends on question it will vary.
No. Don't confuse
No, madam.
this with that, because can you see this diagram here? When I explained this, I told
Yes, ma'am.
that there is Z0, okay. This line impedance is Z0, and here it is a lambda by 4 transmission line, okay. And then between the port 2 and port 3, you have an impedance 2Z0, okay. So this is the generic construction of a
Okay, madam.
what you call Wilkinson power divider. Wilkinson power divider, okay. Now in this case, again, if you try to what you call use the concept of transmission lines, what it should be, 2Z0 multiplied by Z0, okay. Take the square root, so root 2
Root 2.
Z0,
Okay, madam.
okay.
Now clear, madam.
Okay.
Thank you, madam.
Okay. So these were some MCQs. I think I missed something on. Okay, we had discussed about power dividers. So quickly, I'll discuss about directional couplers. So about directional coupler, some of the basic ideas, if you remember. So you have an input port in case of a directional coupler. So this is a input port, and this is say port 2. Most of the textbooks, they refer this to a through port, okay. And this is called as port 3, which is generally called as coupled port. And there is something called as isolated port, okay, or port 4, okay. So the idea of the isolated port is, ideally we should not receive any power in the isolated port, okay. And from the input port, there will be transmission to the through port and also the coupled port, okay. But the coupling is being given by how much it is coupled from port 1 to port 3, okay. So how do we define all these? The coupling is given as the ratio 10 log P1 to P3, okay. How much power is coupled from port 1, that means the input port, to the coupled port, okay. Now next parameter is directivity, okay. So directivity indicates like it's a measure, say some from the input port power is getting coupled, that means this is like a forward way. there is a chance that there is some backward wave which is getting coupled to port 4. There is a chance. Okay, ideally it should not be the case, but there is a chance that there are some backward waves. So how much your directional coupler is good, how good it is, depends on this parameter, the ratio of P3 to P4. So that is your 10 log of P3 by P4. Okay. Now, the next parameter I want to discuss is the isolation. So as I said before, how much power is getting coupled to the isolated port from the input port. Okay. So it's 10 log of P1 to P4. Ideally, no power should get coupled to the isolated port, but here there will be some amount of power. It's in a practical circuit, so we take the isolation. Now, the last parameter to discuss is insertion loss. What do you mean by insertion loss? Say when the power is getting transferred from port 1 to port 2, okay, so that transmission, okay, so that is your insertion loss, 10 log P1 by P2. Okay, so this is all about the directional coupler, and also in a directional coupler, all the 4 ports S11, S22, S33, S44, all the 4 ports are perfectly matched. So we can say the reflection coefficient is 0. In addition to that, it's a reciprocal network. We can say S12 is equal to S21. Say if you use this input at this port and output at through port, and instead if you make this as an input port and measure through port, it will be same. Okay, that is the meaning of this S12 equal to S2. Okay, now quickly some questions on directional coupler. So directivity of a directional coupler signifies direction of power flow in the coupler. Is it the direction? What is this directivity giving us?
Madam, directivity is related to gain only, no, madam?
Yes. So it is
Gain.
basically directivity is the ratio of P3 to P4. So how much power is getting coupled, that means in the port 3 compared to the isolated port. Okay. So it doesn't signify the direction or something. It's signifying the measure of power coupled. Okay. So it's a false statement. We have to say the measure of coupled power to the isolated power. So next question. Isolation of a directional coupler is a measure of. What do you think among the options? So you know what is a coupled port. This is the second port.
Option.
Did you say option A?
Yes, ma'am. A option.
Okay. Yeah, it's option A. So this is the power delivered to the uncoupled port. Okay. So ideally in this port, we don't want any power to get coupled. So it is called as an uncoupled port or isolated port. So the topic of discussions, I think we came across this directional couplers. Okay, microwave filters is something which is pending. So while discussing some question, I'll discuss about the microwave filter also. Okay. look at this problem here. For the circuit shown here, Z1 is chosen that power from port 1 is equally divided between port 2 and port 3. The closest value of reflection coefficient at port 1. So we have to find the reflection coefficient at port 1. If power is getting equally divided between port 2 and port 3. So what will be the condition for that? If we have to equally divide the power between port 2 and port 3. I suggest you please respond, because it will be nice if you could interact. I'll get an idea of if you could, if we are following what I am trying to say. If you want to make the power equal, say, if you remember the basic circuit, it had this Z0, 2Z0 and 2Z0. Then I said power is getting equally divided into port 2 and port 3. So what was the reason? The reason, both the arms are having the same impedance, 2Z0. So what should be the condition here for equal division of power between port 2 and port 3? Please type in the chat if you are unable to mute yourself. Hope I am still online. Am I audible?
Yes, ma'am.
Okay, so my point is, if you want an equal power division between port 2 and port 3, yes, okay, thank you for the response. Yeah, right, Veera Pandu. So it's Z1 is equal to 4Z0. This should be the condition, okay, for equal power division. So if you know that, this has to be equated to 4Z0. Now tell me, these are two impedances coming in parallel. Okay, so let me redraw it for you for the better understanding. 4Z0 and 4Z0 is coming in parallel. Can you tell me what will be the effective impedance here? Four Z0 and 4Z0 coming in parallel, it will be
2Z0.
2Z0. So what will be the reflection coefficient? Now the circuit has reduced. Tell me what will be the reflection coefficient. The very fundamental equation for calculating the reflection coefficient is ZL minus Z0 by ZL plus Z0. Answers, please.
C option.
Yes. It's 1 by 3 or 0.33. I hope this is clear. So let's move to the next question. So the next question is a power divider circuit, as you can see here. The value of Z for which the port 1 is matched. Okay, so this is the port 1. So we are saying that port 1 is matched. So you can notice that when you say port 1 is matched, that means the reflection coefficient is 0. Or I can say it is perfectly matched. Now look at this line. So this two arms. So this is one arm. Okay, I'm just noting it here. This is the second arm. So if you notice here, it is the Z0, and here also it's a Z0, and here you have a 2Z0. Okay, so the Z0 and 2Z0 is there in one arm. Okay, and the two arms, so this is say arm 1 and this is arm 2, and those two are coming in parallel. And you also have at the input line, if you notice, this is the input line. In the input line, you have a lambda by 4 transform. Okay, so first let us think about the arms separately. What will be the impedance in case of first arm and second arm? So it's a combination of 2Z0 and Z0. So 3Z0, 3Z0. And then that is going to come in parallel. Okay. So 3Z0 parallel to 3Z0, which is going to be 3Z0 by 2. And so if you remember, so now this network is going to reduce. You have a lambda by 4 line to which we are connecting what? 3Z0 by 2. Okay. Here, this side of the line, you have Z0. Now, what is the question? Question is on this Z value. Remember, you have a lambda by 4 transformer. So, ZQWT. What is that?
C option.
Yes, right. I hope everybody is getting this. If there are any doubts, please ask. So this is going to be Z0 into 3Z0 by 2. Take the square root. So the answer is going to be root 3 by 2 Z0. Okay, now moving on to the next question. For a resistive power divider shown in the figure, half the input power is dissipated in the resistor. Is it true or false? Half the input power is dissipated in the resistor. Okay, can you tell why it is false or why it is true? Okay, let me tell you this. So there are two resistances. Resistive power divider. In both the arms, you have two resistors. Okay. So basically, the power is divided equally to both, but at the resistor, there is some dissipation. At last, here it is P in by 4, say. And here it is again P in by 4. So, the input power dissipated here is P in by 4. Again, here is P in by 4. So, what is the total power dissipated in the resistor alone? So, that is here P in by 4 and P in by 4. Totally P in by 2. So, half the input power is being dissipated in the resistor. So, it's true. Okay.
Yes, ma'am.
Okay, let's move to the next question. If the resistance connected between port 2 and port 3 of a 3-port equal Wilkinson power divider. Yeah, you remember the Wilkinson power divider? You have a lambda by 4 line. Between the 2 ports, you connect a resistor which is 2Z0 and this is Z0. So it's a 3-port network, 1, 2, and 3. Okay, the question is, suppose if you disconnect, okay, or remove this particular impedance, will the port 1 still remain matched? Or the other way to ask this question is, what is the purpose of the 2Z0? Yes, you are right. Yeah, please go ahead.
2 is not is load impedance.
So why do we connect that 2Z0, or what is the purpose of that 2Z0? Or what is special about the Wilkinson power divider? If you remember S23, S32, I told it is going to 0. So basically it is giving what? Isolation. Okay. So this connected resistor is giving the isolation between port 2 and port 3. Even if that is disconnected, it's not going to affect the matching at port 1. So it is true. But if it is going to be disconnected, then there will be a problem here. S23, S32 cannot remain as 0. So when we say port 1 matching, it is referring to S1. And it has nothing to do with this 2 segment. Hope this is clear. Okay, now we have a question on directional coupler. I would like to tell you, like, it's very important you try out the questions. So please do try. I can give you the equations for coupling and directivity. So looking at this question, please do try. I'll write once again. Coupling is 10 log of P1 by P3 and directivity is 10 log of P3 by P4. Okay, and you are given with directional coupler has a coupling of 20 dB, directivity of 40 dB. So these two numbers are known to you. If 10 dBm power is incident at port 1, so you have an input power which is in terms of dBm. Okay, and assume that all the ports are matched. Okay, what is the power at port 4? That means you have to finally calculate what is P4. Now my first step would be to understand what is this dBm.
Milliwatt.
Yes. So can we make this back to power in milliwatts? Looking at 10 dBm, what is the power in milliwatts? That's my simple question. I suggest you please look back once again. Are you sure it is 0.01? I am asking the power in milliwatts. Okay. So you are given with the power in dBm.
10 milliwatt.
10 milliwatt. Okay, that's the right option. I hope everybody understood how it became 10 milliwatts. So if you just try to understand this, 10 log x is basically 10 dBm. And x is 10 power 1. Okay, so that is going to be 10 milliwatts. We don't write the units here, but just write it like 10 milliwatts. Okay. Oh, so these are very basic things. Okay, let's come back to this. Coupling and directivity. Both are known to you. And you also know what is P1. Let me write it. Let me not use this P in. It's basically P1. So you know coupling and P1. Can you find P3? I request all of you, please do try to find. Somebody said the answer. What is P3?
0.1 milliwatt.
Yes, exactly. 0.1 milliwatts. Now, use the next equation, directivity. Find what is P4.
A option.
Yeah, that's the right option. I'll wait for some more time. Like, if anybody is facing any issues to find it out, let me know. If you want me to solve it. Say coupling is 20 dB, 10 log of P1. P1 value is 10 milliwatts and P3. Okay. So you have this 10 milliwatt by P3 is equal to 10 square. And P3 is equal to 10 by 100, which is 0.1 milliwatts. Similarly, you find P4. Any doubts?
No, madam.
Okay, so let's move on. Okay, so the next two questions are on filters. Okay, before that, I would like to ask you, like, are there any general doubts or queries with respect to the previous assignments or anything in particular about the week content or
Hello, madam.
yes, please.
Madam, last time I told no, madam, that one problem, 0.28. Yeah, so I also sent to your mail, no, madam.
Yeah. We finally we came across that, no? Like I told that it is.
No, madam. No, madam. Your answer is correct, madam. 28 point something. That is correct. Why? Because, madam, that speed
Okay.
of light I didn't convert 10 power
8.
10 centimeter is there, no, madam. I put 10 power 8.
Okay.
But your answer is correct, madam. I done mistakes, madam.
Okay. Then let me just go back and see it once again. I was
Okay, madam.
assuming that it is correct. I mean,
Yes, madam. I sent a mail also, madam, for last Sunday. You have to check it, madam. Once.
Okay, okay, I'll check that. Huh.
Your answer is correct, madam.
Okay, okay, fine, fine. So, with respect to the previous assignments, um, anything, I mean, is it all going good? I mean, we have come to some week 5 already. So, what is that you feel about the course and
Last questions. I will show you question, but I got 6.25 gigahertz, madam. But 5.30 answer is came, madam. Last week.
week 5?
Yes, madam. I will send to mail, but I got answer is that one I will send to madam. Whether I done mistakes, I don't know. That
Okay,
one only later I will send to madam. Remaining all okay, madam. Previous weeks they sent
okay.
assignment solutions also. Two
Yes,
assignment they
yes.
sent
So,
solutions
I
also.
think 3 of them were released.
Three, yes, ma'am. Three of them they released,
So if you
madam.
have anything with respect to 4 and 5, you can ask. Question 1 in assignment 4, is it correct question? Okay. You are referring to assignment 4, huh? Yeah, question 1. Okay, let me just so I hope you are referring to this question. Can you see my slide?
Yes, ma'am.
Okay, so as far as I understand, this is a valid question because we discussed about this L section matching network, and there is a connection between ZL. Oh, okay, so there is something missing here. Okay, real part of ZL is okay greater than Z0, that is missing in this statement. Okay, okay, I understand. Okay. Okay, so I suggest, yeah, I understood that. So I suggest you please write in the discussion forum. I hope you know about the discussion forum. Can you see this tab here? Ask a question.
Yes, ma'am.
So I suggest you please write in this ask a question with the reference to assignment 4 question 1. See, people have written different things. I mean, discussion forums, whatever comes, we are taking into consideration of those things. I am not the one who deals with the assignment part. So I am the one who deals with the problem solving sessions, but I will try to inform the respective people. But my suggestion is to please write in this ask a question also, so that it is brought to the notice immediately. And if there are any mistakes, definitely it will be re-evaluated. So there is a particular amount of time wherein you have all these kind of discrepancies, you can say, and within that time the TS will look at those discrepancies and re-evaluate all these. Although right now you might have got the score, but nothing to worry, later it will be re-evaluated.
Madam, same thing.
Huh.
Madam, assignment 5, madam, 7th questions. The I got answer is 5.1 second, madam. I will check it. 6.25. Madam, 6.25, but answer is a 5.30 correct answer, but I got 6.25 only.
Okay,
That seventh
I'll
question,
try
madam.
to redo that.
Okay, madam, that.
This is okay, 5.3. You got the answer of 6.25, right?
Yes, ma'am.
Okay, I'll get back to you on this.
Okay, madam.
You can just send me a reminder by any chance if I miss it. Please send me a reminder in the email.
Okay. Now, no problem, madam. Remaining all clear, madam. Only one.
Okay, okay, fine. Okay, now we'll go back to some questions on filters. Uh, I have two more questions left. Yeah. So about filters, I hope. Yeah, before going to filters, I had something to talk about this directional couplers to give a just one extra something which we missed to discuss is about the two-hole directional coupler. So I hope you remember this waveguide based two-hole directional coupler working principle, wherein you have seen that there are two apertures like a hole. So this is one aperture and this is the second aperture. Basically, these are two waveguides. This is a waveguide, this is another waveguide combined together. You have two apertures. So let me call this as 1 and 2. Okay. And the distance between the two, okay, this is going to be lambda g by 4, where lambda g is the guide wavelength. So in a two-hole directional coupler, this distance will be 1/4 of the guide wavelength. And this will ensure that the phase at this at the point 1 and 2 to differ. Okay. So delta phi, I mean, say, if this is D, what will be the phase, corresponding phase between, or I can say what will be the phase difference between 1 and 2. So that will be beta times D. Okay, that is the phase. So if you know the D, that is the separation, then beta times D is the phase. So if, for example, if this is say BF, okay, say amplitude BF with angle 0, assume that, okay, then at this point it will be BF e raised to minus J beta D, okay, and this phase difference is going to depend on what? The length, depend on D, that is nothing but the lambda G by 4, okay. So this I wanted to convey. So what will be the phase difference here? 2 pi by lambda into lambda by 4. So it will be pi by 2. So the phase difference will be such that it is 90-degree out of phase in case of a two-hole directional coupler. I don't have any questions with that. Just wanted to tell the concept. Okay. Now moving on to filters. So in filters, you have come across this Butterworth filter, Chebyshev filter, and also I believe this linear phase filter. Okay. So, and I hope you could gather something wide, the significance of each of these filters. Say if you want the minimum insertion loss and maximally flat response, which among these would you choose? Is it a Butterworth, Chebyshev, or a linear phase filter? If you want a minimum insertion loss and maximally flat response, which among these would you choose? Yes, right option. It's a Butterworth filter. Now, suppose if you want a better phase response, which one among these would you choose for a better phase response?
Linear phase.
Yes, linear phase, as the name suggests. Okay. Now, only Chebyshev is left out. Can you tell what is the speciality of anything specific about the Chebyshev filter? What is so special about that?
Tapering.
Yes.
Tapering.
Yeah. Please complete your sentence. Yeah. I couldn't hear.
More ripples.
Ripples. Exactly. Yes, that is right. You have ripples, and are they in the pass band and stop band? Yes, they are both present. There are ripples in pass band and stop band both. Okay. And also, if you remember, if you need a sharp cutoff frequency, you have to choose a Chebyshev filter, for a sharp cutoff frequency. Okay. Now, okay, with that kept in mind, let us look at these questions. Say, my maximally flat low pass filter is required to be designed with a cutoff frequency of 3 gigahertz. So, this is the cutoff frequency 3 gigahertz and at least 20 dB insertion loss at 6 gigahertz. So, I have an operating frequency which is 6 gigahertz. And it is mentioned that the insertion loss is 20 dB. Now, can you calculate the order of the filter? So, this you can do with the equation for insertion loss. So, insertion loss is given by 10 log of 1 plus omega by omega c the whole raised to 2n, where omega is the operating frequency, omega c is the cutoff frequency, and n is the order of the filter, IL is the insertion loss. Can you try to find it out? What is n? So omega by omega c ratio is same as f by fc ratio. So this turns out to be a simple question. In the sense, you can solve it soon. If anybody has got the answers, I suggest you please type in the chat or unmute yourself. So omega by omega c will be f naught by fc. Anybody with the answers? It should be 2. So the insertion loss is 20
2.3.
2.3. Can you please recalculate? Any answers? So this comes out to be 1 plus 2 raised to 2n is 10 square, which is 100.
3.3, ma'am.
Yes, right. So finally, you will get. So I hope you know how to solve it. 2 raised to 2n is 99. So take logarithm on both the sides. 2n log 2 is equal to logarithm of 99. So n will be 3.3. So you can't give an order as 3.3. So you have to round off to the next integer. So it's a 4. Hope this question is clear.
Yes, ma'am.
Okay. So I hope I can move to the next. So coming to the next question. Yeah, something I missed here. Okay, I wanted to ask you. Here it is mentioned maximally flat low pass filter. So could you say whether it is Butterworth or Chebyshev?
Butterworth.
Yes, Butterworth. And coming to this question again, it's a second order. So order is given, and again this is maximally flat. So Butterworth filter, it's a low pass filter. Okay, designed with a cutoff frequency of 2 gigahertz. So this is FC, and the source impedance is say ZS or something. I can denote 50 ohm. Value of the capacitance to be used in the low pass filter. So to do this question, you should know how do we realize a low pass filter prototype. So if you would have gone through the lectures, I hope you remember the prototype. How do we say? You have this RLC and again C, and again you have okay. So if you remember, this is denoted as G0, G1, G2, G3, and last element will be Gn plus 1. So if you say the order is 2, then the last element will be what? G3. That means it stops here. Okay. Okay, now what is the question? You know the cutoff frequency, 2 gigahertz. And you also know the source impedance, that is ZG, okay? ZG or ZS or whatever it is, 50. It's not same as G0, please don't confuse. G0 is 1, okay? So if you have gone through, please go through this LPF realization. Okay, and this one, if you notice, this starts with a shunt element. Okay, what is the shunt element here? That's a G1, that's a capacitance, starts with a capacitance. There is another realization which starts with a series element. how do we denote it? Series element means you should have the current source, you should have a parallel resistor. Current source means you will have a parallel resistor. Then start with the series element. Okay. Then L, C, then again L, and go on. And the last element will be Gn plus 1. Okay. So this is G0 equal to 1. This is G1, G2, G3, and so on. Okay. So this is with the series element in start, and this is with the shunt element in start. Now, the question is about what is the value of capacitance to be used in the particular LC, low pass filter. Okay. To do that, you have to get the expression for G1 and G2. If you have gone through the lectures, you have come across a chart wherein based on the order of the length or order of the filter, you can find the value of G1 and G2. Okay. So once if you have the G1, so this is from a chart. Okay, I'm not writing it directly. So this is from a chart. It is 1.4142. So G1, G2 value is known to you. So once if you know G1, okay, can you back calculate the capacitance? There is an expression for that. Okay. C is G1 by Z0 into omega C. G1 value is known to you. Z0 value is known to you. And omega C is basically the cutoff frequency. Then you can calculate the capacitance. Any answers?
B option.
B or D? I couldn't hear properly.
B for Bombay.
Okay, B. Yeah. That's the right option. So 1.4142 by 50 into 2 pi into Fc is 2 gigahertz. So if you solve, you will get 2.25 picofarad. I hope this is clear. Any doubts? So that's all I have got for today's session. So if you have any questions, please do ask. Basically, I always try to make a session for 1.5 hours, so that if you have any additional questions or you can ask those things, and we try to solve those kind of issues if you have any.